Right now, as you're watching this, humanity consumes approximately 20.6 terawatts of power. That's enough energy to light up 188 billion LED bulbs simultaneously, to power every device on Earth, to fuel our entire technological civilization. It sounds impressive, doesn't it? But here's what should make you pause in absolute wonder. That enormous number represents barely 0.7 on a scale that measures the true potential of intelligent civilizations. We're not even at level 1 yet. Tonight, we're embarking on a journey that will fundamentally change how you see humanity's place in the cosmos. We're exploring the Kardashev Scale, a framework so profound it transforms our understanding of what technological civilizations can achieve. By the time we're finished, you'll see that everything we consider advanced today is merely the opening chapter in a story that could span millions of years and encompass entire galaxies. Before we dive into this cosmic roadmap together, I'd love to know where you're tuning in from tonight and what keeps you wondering about humanity's ultimate destiny among the stars. And if you find yourself fascinated by these grand visions of our species' future, I'd be grateful if you gave this video a like and perhaps subscribe to join our community of cosmic visionaries. Get ready. The journey begins now. The year was 1964, and Soviet astrophysicist Nikolai Kardashev was facing one of the most profound questions in all of science. As he scanned radio signals from deep space, searching for evidence of extraterrestrial intelligence, he realized something extraordinary. If alien civilizations existed out there among the stars, how would we even recognize them? What would advanced intelligence look like on a cosmic scale? Kardashev's brilliant insight was to recognize that energy consumption might be the universal signature of technological advancement. No matter what form alien intelligence might take, no matter how different their biology or culture might be from ours, they would all face the same fundamental challenge that drives every aspect of technological development: the need for energy. From this deceptively simple observation, Kardashev constructed a scale that would revolutionize how we think about civilizational progress. He proposed that we could classify any technological civilization based on the total amount of energy they could harness and utilize. This wasn't just about counting power plants or measuring electricity consumption. This was about understanding the fundamental relationship between energy mastery and cosmic significance. The scale he developed divides civilizations into 3 primary categories, each representing a quantum leap in capability and cosmic influence. Type 1 civilizations harness all the energy available from their home planet. Type 2 civilizations capture and utilize the entire energy output of their star. And Type 3 civilizations command the energy resources of one of billions of stars. But here's what entire galaxy, with all its hundreds, makes this framework so fascinating and so unsettling. When Kardashev applied his scale to human civilization, he discovered something remarkable. Despite all our technological achievements, despite our nuclear reactors and solar panels and wind farms, we hadn't even reached Type 1 status. We were stuck at what researchers now call Type 0, a pre-planetary civilization still dependent on the organic remains of ancient life forms for most of our energy needs. Today, more than half a century after Kardashev first proposed his scale, humanity has progressed to approximately Type 0.7276. That decimal might seem insignificant, but it represents the entire sweep of human technological development from the agricultural revolution through the digital age. Every steam engine, every power plant, every solar panel humanity has ever built has contributed to moving us from roughly 0.6 to our current position. Yet we're still not even halfway to becoming a true planetary civilization. And the mathematics of the Kardashev scale reveal why this journey is more challenging than most people realize. This isn't a linear progression where each step takes the same amount of effort. the scale is exponential. To progress from our current type 0.73 to type 1, civilization requires approximately 500 times more energy than we currently consume. Every decimal point on the scale represents roughly 1,000 times more energy than the previous level. Think about what this means for humanity's future. If we maintain our current growth rate in energy consumption, which has averaged about 3% annually throughout the modern era, reaching type 1 status could take anywhere from centuries to millennia. But the exponential nature of the scale means that even small changes in our rate of progress can dramatically alter these timelines. The transition to type 1 civilization represents humanity's graduation to true planetary stewardship. A type 1 civilization consumes power on the order of 100 trillion watts, roughly 100,000 times our current planetary output. This level of energy mastery would fundamentally transform human capabilities and our relationship with Earth's natural systems. Picture what type 1 humanity might look like. We would possess the technological sophistication to control weather patterns, preventing natural disasters before they could threaten human populations. Volcanic eruptions, earthquakes, hurricanes, all of these would become manageable phenomena rather than catastrophic forces beyond our control. The energy sources that would enable such capabilities stretch far beyond our current renewable technologies. A Type 1 civilization would likely master nuclear fusion, the same process that powers the sun, providing virtually unlimited clean energy. Advanced fusion reactors could convert hydrogen, the most abundant element in the universe, directly into usable power without the radioactive waste associated with current nuclear fission technology. But fusion alone might not be sufficient. Type 1 civilizations might also harness matter-antimatter annihilation, the most efficient energy conversion process known to physics. When matter and antimatter collide, they convert directly into pure energy. According to Einstein's famous equation, E=mc², a single gram of antimatter reacting with a gram of ordinary matter releases the energy equivalent of a 43 kiloton nuclear weapon, but in a controlled, usable form. The infrastructure required for Type 1 civilization would likely include massive space-based solar collection systems orbiting Earth or positioned at gravitationally stable Lagrange points. These orbital power stations could collect solar energy without atmospheric interference and beam it back to Earth using microwave transmission. The scale of such systems would dwarf any current human construction project, potentially involving thousands of satellite arrays working in coordination. Yet even as we contemplate these extraordinary possibilities, we must confront the sobering reality of the challenges ahead. The transition to Type 1 status isn't just a matter of building more power plants. It requires navigating what might be the most dangerous period in human history. Consider the environmental constraints that emerge as energy consumption approaches planetary limits. If humanity maintains its historical 3% growth rate in energy production, by the year 2300 our energy budget will equal the total power received by Earth from the Sun. At that point, all forms of energy ultimately return to the biosphere as heat, potentially rendering our planet uninhabitable. This represents what researchers call the Type 1 bottleneck. Successfully navigating this transition requires not just massive increases in energy production, but revolutionary advances in energy efficiency and heat management. We would need unprecedented global cooperation, environmental stewardship, and technological innovation to maintain planetary habitability while dramatically expanding energy utilization. The stakes couldn't be higher. Some scientists speculate that the transition from Type 0 to Type 1 carries a strong risk of civilizational collapse. Species that cannot solve the coordination problems required for planetary scale energy management might destroy themselves before achieving true Type 1 status. This could explain why we haven't detected obvious signs of alien civilizations despite the vast number of potentially habitable worlds in our galaxy. But let's assume humanity successfully navigates these challenges. Let's imagine we develop the wisdom and technology necessary to become a stable Type 1 civilization. What comes next represents a leap in ambition that makes our current space programs seem quaint by comparison. Type 2 civilization requires harnessing the energy of our star itself. The Sun produces approximately 3.8 times 10 to the power of 26 watts of power, roughly 10 billion times more energy than a Type 1 civilization can access from planetary resources alone. Capturing even a fraction of this stellar output would provide energy resources beyond anything our planet-bound existence could imagine. The concept most associated with Type 2 civilizations is the Dyson sphere, named after physicist Freeman Dyson, who explored the idea in his influential 1960 paper. Dyson speculated that such structures would be the logical consequence of the escalating energy needs of a technological civilization and would be a necessity for its long-term survival. But the popular image of a solid shell surrounding the Sun represents just one possible approach, and arguably the least practical one. The material requirements for such a structure would be staggering. A Dyson sphere in our solar system would have a radius of 1 astronomical unit, roughly 150 million kilometers, and a minimum surface area 600 million times greater than Earth's surface. The gravitational instabilities and structural stresses involved make solid shells largely impractical using any known materials. Instead, Type 2 civilizations would more likely construct what researchers call Dyson swarms. These would consist of millions or billions of individual solar collecting satellites orbiting the star in coordinated formations. Each satellite would capture solar energy and either beam it to collection points or store it for local use. The swarm approach offers several advantages over solid shells. It's more feasible to construct gradually, it's less vulnerable to catastrophic failure, and it can be optimized for specific energy collection requirements. Alternative designs include Dyson bubbles, which utilize solar sail technology to maintain stationary positions around the star. These thin, reflective sheets would be propelled by radiation pressure, allowing them to hover at fixed points relative to the star while collecting and redirecting energy. However, this approach requires advanced materials with exceptional strength-to-weight ratios to withstand the immense forces involved. The construction of any Dyson-type structure would represent the most ambitious engineering project in human history, dwarfing every previous construction effort combined. The logistics alone would require revolutionary advances in automated manufacturing, space transportation, and artificial intelligence capable of coordinating activities across solar system scale distances. Consider the material requirements. Building even a partial Dyson swarm might necessitate the complete disassembly of entire planets to provide raw materials. Mercury, with its proximity to the Sun and lack of atmosphere, is often cited as a prime candidate for such resource extraction. Advanced self-replicating robotic systems would likely be essential, capable of converting raw planetary material into the sophisticated components needed for solar collection satellites. The energy benefits of achieving Type 2 status would be transformative beyond current human comprehension. With access to stellar-scale energy resources, Type 2 civilizations could engage in large-scale stellar engineering projects. They might construct artificial planetary systems, move planets between star systems, or even manipulate stellar evolution itself. Nothing known to science could threaten such a civilization. Asteroid impacts, supervolcanic eruptions, even the collision of moon-sized objects with Earth would be manageable problems rather than existential threats. Type 2 civilizations would possess the energy resources necessary for serious interstellar exploration and colonization. While they would still be constrained by the speed of light, they could construct vast networks of self-replicating probes capable of exploring stellar regions spanning hundreds of light years. These probe networks could establish the foundation for eventual expansion to multiple star systems, setting the stage for the ultimate achievement in the Kardashev framework. The search for evidence of Type 2 civilizations has become a significant focus of modern SETI research. Dyson spheres or swarms would produce distinctive signatures in the electromagnetic spectrum. They would absorb stellar energy across visible wavelengths and re-radiate it in the infrared spectrum. Astronomers now actively search for stars with unusual infrared signatures that might indicate artificial energy collection and reprocessing. Several intriguing candidates have emerged from these searches. The star KIC 8462852, discovered by citizen scientists in 2015, exhibited unusual light fluctuations that briefly sparked speculation about possible megastructures. More recently, astronomers have identified 7 M-dwarf stars within 1,000 light-years of Earth that show anomalous infrared signatures. While alternative explanations involving natural astrophysical phenomena remain more likely, these discoveries demonstrate both the potential detectability of Type 2 civilizations and our growing capability to search for them. The timeline for humanity's potential progression to Type 2 status stretches far beyond Type 1 development. Even with revolutionary breakthroughs in energy technology, the construction of Dyson-scale infrastructure would likely require thousands of years and represent the coordinated effort of multiple generations. The project would test not just our technological capabilities, but our capacity for long-term thinking and sustained cooperation across centuries or millennia. Yet the rewards would justify such extraordinary efforts. Type 2 civilization would mark humanity's transformation from a single planet species to true stellar engineers, capable of reshaping solar systems according to our needs and values. We would possess the energy resources necessary to support populations numbering in the trillions, to terraform worlds throughout our solar system, and to begin the long journey toward our species' ultimate destiny. Because beyond Type 2 lies an achievement so vast it challenges human imagination. Type 3 civilization represents mastery over an entire galaxy, commanding the energy output of hundreds of billions of stars. The scope of such civilizations transcends anything in our current experience, representing technological capabilities that would appear godlike to species at our current level of development. The energy output they would command staggers the imagination. Between 10 to the power of 36 and 10 to the power of 37 watts, flowing through systems spanning hundreds of billions of light years. To put this in perspective, a Type 3 civilization would have access to roughly 10 billion times more energy than even the most advanced Type 2 civilization could harness from a single star. But how does a civilization make the leap from stellar engineering to galactic dominance? The transition from Type 2 to Type 3 represents perhaps the most profound transformation in the entire Kardashev framework. It's not simply a matter of scaling up existing technologies. It requires fundamental breakthroughs in faster-than-light communication, if not travel, and coordination systems capable of managing projects across distances that light itself takes tens of thousands of years to traverse. Consider the logistical challenges alone. Our Milky Way galaxy spans roughly 100,000 light-years from edge to edge. A signal sent from one side of the galaxy to the other would take 100,000 years to arrive, assuming it travelled at light speed. Coordinating the construction of Dyson swarms around billions of stars would require either accepting these enormous communication delays or discovering new physics that allows information to travel faster than light. The most likely path to Type 3 status would involve gradual expansion outward from the home star system. A mature Type 2 civilization would launch self-replicating probe networks to nearby star systems, each probe carrying the blueprints and manufacturing capabilities needed to construct solar collection infrastructure around distant stars. These probes would replicate themselves using local materials, spreading the civilization's energy harvesting capabilities from star to star in an expanding sphere of influence. The mathematics of this expansion are both encouraging and sobering. Even traveling at a significant fraction of light speed, say 10% of the speed of light, it would take roughly 1 million years for probes to reach and develop the most distant stars in our galaxy. But once the infrastructure was in place, the civilization would have access to energy resources that dwarf anything we can currently imagine. Type 3 civilizations wouldn't limit themselves to harvesting stellar energy. They would likely tap into even more exotic sources of power that exist on galactic scales. Supermassive black holes, the gravitational monsters that lurk at the centers of galaxies, represent energy sources that make even the largest stars seem modest by comparison. Our galaxy's central black hole, Sagittarius A, contains the mass of approximately 4 million suns compressed into a region smaller than our solar system. The accretion disk surrounding such a black hole glows with temperatures reaching millions of degrees, radiating energy across the electromagnetic spectrum. But the real prize lies in the black hole's rotational energy. A spinning black hole drags space-time itself around with it, creating a region called the ergosphere, where it becomes theoretically possible to extract energy directly from the black hole's rotation through a process called the Penrose mechanism. Advanced Type 3 civilizations might construct massive orbital stations around galactic centers designed to harvest this rotational energy. They could drop carefully engineered objects into the ergosphere, allowing them to gain energy from the black hole's rotation before ejecting them back out with more energy than they started with. The black hole would slowly lose rotational energy in the process, but the amounts available are so vast that such extraction could continue for trillions of years. The technological signatures of Type 3 civilizations would be visible across intergalactic distances. Imagine looking at our galaxy from the Andromeda Galaxy, 2.5 million light-years away. A mature Type 3 civilization would have fundamentally altered the electromagnetic spectrum of the entire Milky Way. Instead of the natural light curves we expect from stellar evolution, we might see artificial patterns optimized for energy collection and utilization. Entire star systems might be dimmed or missing from the visible spectrum as Dyson swarms captured their energy output and converted it to infrared radiation. The galactic center might show signs of massive engineering projects designed to harvest black hole energy. Even the overall shape of the galaxy might be artificially modified, with stellar orbits adjusted to optimize energy collection or facilitate transportation networks spanning tens of thousands of light years. Current SETI researchers are beginning to search for such signatures, looking for galaxies that show anomalous energy distributions that might indicate the presence of Type 3 civilizations. The challenge lies in distinguishing artificial modifications from natural astrophysical processes. Galaxies are already incredibly complex systems with active galactic nuclei, stellar formation regions, and gravitational interactions that can create unusual energy distributions. But some theoretical models suggest that Type 3 signatures might be unmistakable once we know what to look for. A galaxy fully developed by a Type 3 civilization might show infrared emission patterns that are simply impossible to explain through natural processes. The statistical distribution of stellar brightness, the spectrum of the galactic center, even the galaxy's interaction with neighboring galaxies might all bear the fingerprints of intelligence operating on cosmic scales. The timeframes involved in reaching Type 3 status stretch beyond anything in human historical experience. Even with the most optimistic projections, the transition from Type 2 to Type 3 would likely require hundreds of thousands to millions of years. This represents thousands of human generations, assuming we maintain anything resembling current lifespans. The project would require not just technological capability, but unprecedented cultural stability and continuity of purpose across timescales that dwarf all of recorded human history. This raises profound questions about the nature of intelligence and consciousness at such scales. Would a Type 3 civilization still be recognizably human in any meaningful sense? The beings managing galactic scale projects might be so enhanced, either biologically or technologically, that they would be as different from us as we are from single-celled organisms. They might exist as vast collective intelligences distributed across multiple star systems with individual components that live for thousands or millions of years. Alternatively, they might have transcended biological existence entirely, existing as pure information patterns capable of moving between different physical substrates at will. The distinction between artificial and biological intelligence might become meaningless at Type 3 scales, with consciousness itself becoming a technology that can be engineered, optimized, and scaled according to the civilization's needs. The energy resources available to Type 3 civilizations would enable projects that approach the limits of what physics allows. They might construct artificial galaxies, creating stellar nurseries where new stars are born according to carefully planned specifications. They could build galaxy-spanning transportation networks, possibly exploiting exotic phenomena like wormholes or other space-time manipulations that remain theoretical to our current physics. The ultimate expression of Type 3 capability might be the ability to influence cosmic evolution itself. Such civilizations could potentially trigger or prevent galactic collisions, manipulate the large-scale structure of space-time, or even influence the expansion rate of the universe within their region of influence. They would become active participants in cosmic evolution rather than passive observers, shaping the development of the universe according to their values and objectives. But perhaps the most intriguing possibility is what lies beyond Type 3. Kardashev's original scale ended with galactic civilizations, but subsequent researchers have proposed extensions that stretch toward even more cosmic achievements. Type 4 civilizations might harness the energy of multiple galaxies or entire galactic clusters. Type 5 civilizations could potentially access the energy resources of the entire observable universe. At such scales, the distinction between intelligence and the fundamental forces of physics might disappear entirely. A Type 5 civilization would possess the energy resources necessary to influence the basic parameters that govern reality itself. They might be able to adjust the strength of fundamental forces, alter the rate of cosmic expansion, or even create new universes with physical laws optimized for the emergence and flourishing of consciousness. These speculative extensions of the Kardashev scale venture into territory where science blends with philosophy and imagination, but they serve an important purpose in helping us understand the ultimate trajectory of technological development. If intelligence and energy mastery continue to grow exponentially, there might be no natural upper limit to what conscious beings can achieve given sufficient time and resources. The search for evidence of such advanced civilizations represents one of the most profound challenges in modern astronomy. We're looking for signs of intelligence operating on scales so vast that we might not even recognize them as artificial. The very structure of the cosmic web, the distribution of matter and energy across the largest scales we can observe, might bear the fingerprints of civilizations so advanced that they've become indistinguishable from natural forces. This perspective transforms our understanding of humanity's place in the cosmic hierarchy. We're not just a young civilization learning to harness planetary energy. We might be the earliest stages of a process that could ultimately reshape reality itself. Every fusion reactor we build, every solar panel we install, every step toward greater energy efficiency moves us infinitesimally closer to capabilities that could influence the fate of the universe. The timeline for humanity's progression up the Kardashev scale remains highly speculative, but recent projections offer some intriguing possibilities. Conservative estimates suggest we might reach Type 1 status within the next few centuries, assuming continued technological progress and successful navigation of current challenges like climate change and resource depletion. The transition to Type 2 could occur within a few thousand years if we develop the necessary space-based manufacturing and transportation capabilities. Type 3 status remains much more distant, likely requiring hundreds of thousands of years, even under optimistic scenarios. But these timeframes assume linear technological progress, and history shows us that breakthrough discoveries can dramatically accelerate development. The invention of nuclear power, integrated circuits, or the internet each represented discontinuous leaps that transformed human capability in ways that would have been difficult to predict just decades earlier. Future breakthrough technologies could similarly compress the timeline for advancement up the Kardashev scale. The development of true artificial general intelligence could accelerate research and development across all technological domains. Breakthroughs in materials science might enable construction projects currently considered impossible. Discoveries in fundamental physics could reveal new energy sources or methods of space-time manipulation that dramatically reduce the resources required for stellar or galactic engineering. The key insight from Kardashev's framework is that energy mastery represents the fundamental driver of civilizational capability. Every other achievement, from interstellar travel to consciousness uploading to universe creation, ultimately depends on having access to sufficient energy resources. The scale provides a roadmap not just for technological development, but for the evolution of intelligence itself toward cosmic significance. As we stand at our current position of Type 0.7276, looking up at the vast hierarchy of cosmic achievement that stretches before us, we face a choice that will determine the ultimate trajectory of human civilization. Will we successfully navigate the challenges of planetary energy management and begin the long journey towards stellar and galactic engineering, or will we remain forever bound to our single world, a brief flicker of consciousness in the cosmic darkness? The answer depends on the choices we make in the coming decades and centuries. Every decision about energy policy, space exploration, and technological development contributes to determining whether humanity will join the ranks of cosmic civilizations or remain a footnote in the universe's vast story. The mathematics become even more staggering when we consider the exponential nature of progression beyond our galaxy. Recent theoretical work suggests that Type 3 civilizations might represent merely the beginning of cosmic scale intelligence, not its culmination. Extensions of Kardashev's framework propose Type 4 civilizations that command the energy resources of entire galactic clusters, and Type 5 civilizations that could theoretically access the power output of the entire observable universe. These speculative categories venture into territory where physics blends with philosophy, but they illuminate something profound about the trajectory of technological developments. If consciousness represents the universe's method of understanding itself, then the progression up the Kardashev scale might represent the cosmos gradually awakening to its own potential. Consider what Type 4 capability would entail. Our local galactic group contains over 80 galaxies spanning roughly 10 million light-years. A civilization capable of harnessing the energy output of this entire region would command approximately 10 to the power of 45 watts of power. Such beings would possess the resources necessary to manipulate space-time on scales that encompass multiple galaxies, potentially creating artificial galactic clusters or engineering cosmic structures that span tens of millions of light-years. The coordination challenges alone stretch the imagination. Managing projects across such distances would require either accepting communication delays measured in millions of years or discovering physics beyond our current understanding. Perhaps Type 4 civilizations develop forms of consciousness so radically different from our own that conventional concepts of communication and coordination become irrelevant. They might exist as distributed intelligences that span multiple galaxies with individual components that persist for millions of years while participating in collective projects that unfold over geological epochs. But let's return to more immediate considerations. The path from our current Type 0.73 status to even Type 1 civilization faces challenges that could determine whether humanity ever progresses beyond planetary scale energy utilization. The next century represents perhaps the most critical period in our species' development, as we attempt to navigate what researchers call the Great Filter. The Great Filter hypothesis suggests that somewhere along the evolutionary path from simple life to galactic civilization, there exists a barrier so difficult to overcome that it eliminates virtually all species before they can achieve cosmic significance. The transition from Type 0 to Type 1 civilization represents one of the most likely candidates for this filter, as species must learn to manage planetary scale energy systems without destroying their biosphere in the process. Current projections show humanity reaching approximately Type 0.74 by 2060, assuming continued technological progress at historical rates. This seemingly modest advancement would represent the successful integration of fusion power, advanced renewable energy systems, and perhaps the early deployment of space-based solar collection networks. But the transition to true Type 1 status requires not just technological breakthroughs, but unprecedented global cooperation and environmental stewardship. The environmental bottleneck becomes acute as energy consumption approaches the total solar energy received by Earth. Every form of energy we use ultimately converts to heat, and excessive waste heat could potentially trigger runaway climate effects that render our planet uninhabitable. Successfully navigating this challenge requires revolutionary advances in energy efficiency, heat management, and possibly the relocation of energy-intensive industries to space-based facilities. The development of orbital manufacturing and energy production represents humanity's most likely path through the Type 1 bottleneck. Space-based solar collectors could harvest energy without adding heat to Earth's biosphere, while orbital factories could produce the materials needed for expanding our energy infrastructure without contributing to planetary pollution. The construction of such facilities would require advances in space transportation, automated manufacturing, and artificial intelligence that approach the capabilities needed for eventual Dyson sphere construction. Artificial intelligence might prove crucial not just for managing complex energy systems, but for maintaining the long-term thinking necessary for multi-generational projects. The timescales involved in advancing up the Kardashev Scale exceed human lifespans by orders of magnitude. Successfully coordinating projects that span centuries or millennia might require artificial intelligences capable of maintaining consistent goals and values across time periods that encompass the rise and fall of entire human civilizations. The development of such AI systems presents both opportunities and risks that could determine humanity's ultimate fate. Aligned artificial intelligence could serve as the institutional memory and coordination mechanism necessary for cosmic scale projects. But misaligned AI could represent an existential threat that prevents us from ever reaching Type 1 status. The window for solving the AI alignment problem might be narrower than the timeframe required for major energy infrastructure development, creating a race between technological capability and technological wisdom. Consider the specific technologies that would characterize humanity's progression toward Type 1 civilization. Nuclear fusion represents perhaps the most crucial breakthrough, as it provides the energy density necessary for both planetary power systems and eventual space-based infrastructure. Current experimental reactors like ITER demonstrate the feasibility of sustained fusion reactions. But commercial fusion power requires advances in plasma control, materials science, and energy conversion efficiency that remain decades away. Advanced materials represent another critical bottleneck. The construction of space-based energy systems requires materials with strength-to-weight ratios far exceeding anything currently available. Carbon nanotubes and graphene show promise, but manufacturing these materials at the scales needed for orbital infrastructure remains prohibitively expensive. Breakthrough advances in nanotechnology and molecular manufacturing could potentially solve these material constraints, while simultaneously enabling the self-replicating robotic systems needed for large-scale space construction. The transition to space-based manufacturing would fundamentally transform human civilization even before we achieve full Type 1 status. Access to the vast material resources of asteroids and other celestial bodies would eliminate scarcity for most raw materials, potentially ending resource-based conflicts and enabling unprecedented expansion of human population and capability. The asteroid belt alone contains enough metal to construct orbital habitats supporting populations in the trillions. But space development also introduces new categories of risk that could threaten human survival. The militarization of space could create conflict scenarios that dwarf any terrestrial war, with kinetic weapons capable of destroying entire cities or continents. Space-based manufacturing could enable the construction of weapon systems so powerful they make nuclear arsenals seem primitive by comparison. Successfully managing these risks requires international cooperation and arms control agreements that may be difficult to achieve given the competitive dynamics of space development. The psychology of Type 1 transition presents equally complex challenges. Human beings evolved for life in small tribal groups operating on immediate timescales. The long-term thinking and global cooperation required for planetary energy management represents a fundamental shift in consciousness that our species has never attempted. Educational systems, cultural institutions, and governance structures all need to evolve to support the mindset required for multi-generational cosmic projects. Some researchers suggest that the transition to Type 1 civilization might require fundamental changes in human nature itself. Genetic engineering or cybernetic enhancement could potentially extend human lifespans to centuries or millennia, allowing individuals to personally oversee long-term projects rather than relying on institutional continuity across generations. Brain-computer interfaces might enable forms of collective decision-making that transcend the limitations of individual human cognition, but such enhancements introduce their own risks and uncertainties. Would enhanced humans still share the values and motivations that define our species today? The beings who eventually construct Dyson spheres might be so different from current humanity that they would be unrecognizable as our descendants. The transition up the Kardashev scale might represent not just technological advancement, but the evolutionary transformation of intelligence itself. The search for evidence of Type 1 civilizations in our galaxy provides sobering perspective on these challenges. Despite decades of SETI research and the discovery of thousands of potentially habitable exoplanets, we have found no conclusive evidence of even Type 1 level technology. This could mean that Type 1 transitions are extraordinarily rare, that most species destroy themselves before achieving planetary energy mastery, or that advanced civilizations deliberately hide their existence from younger species like ourselves. The implications of each possibility profoundly shape how we should approach humanity's own development. If Type 1 civilizations are rare, then we might be among the first species in our galaxy to attempt this transition, making our success or failure significant not just for humanity, but for the evolution of intelligence in the cosmos. If advanced civilizations are deliberately hidden, then our own development might be under observation by entities whose capabilities we cannot comprehend. Recent advances in exoplanet detection have revealed that potentially habitable worlds are far more common than previously believed. The Kepler Space Telescope identified thousands of planets in their stars' habitable zones, while the James Webb Space Telescope has begun analysing the atmospheric compositions of distant worlds. If life emerges readily on such planets, then the absence of detectable Type 1 civilizations suggests that the transition from biological evolution to technological mastery might be extraordinarily difficult. The atmospheric signatures that would characterize Type 1 worlds provide specific targets for future observations. Advanced industrial processes would produce distinctive chemical fingerprints in planetary atmospheres, while large-scale energy production would create heat signatures detectable by infrared telescopes. Space-based infrastructure would reflect and absorb starlight in patterns that differ from natural atmospheric or geological processes. As our observational capabilities continue to improve, we might soon detect the first confirmed examples of Type 1 civilizations, providing crucial insights into the feasibility and characteristics of planetary energy mastery. Such discoveries would fundamentally alter our understanding of our own prospects and the prevalence of intelligence in the universe. The timeline for humanity's progression toward Type 1 status remains highly uncertain, but current trends suggest we're approaching several critical decision points. The next few decades will likely determine whether we develop fusion power, establish sustainable space-based manufacturing, and create the international institutions necessary for managing planetary energy systems. These developments would set the stage for the centuries-long process of constructing the infrastructure needed for true Type 1 capability. But even successful navigation of the Type 1 transition would represent only the first step in a journey that could span millions of years. The progression from planetary to stellar engineering represents an even greater leap in scope and ambition, requiring technologies and organizational capabilities that strain current human imagination. The construction of Dyson swarms around our Sun would dwarf every human construction project in history combined. Current estimates suggest that such a project would require the complete disassembly of several rocky planets to provide the necessary materials. Mercury, with its proximity to the Sun and high metal content, represents the most likely candidate for such resource extraction. The engineering challenges involved in planetary disassembly and orbital construction stretch far beyond current technological capability. Self-replicating robotic systems would need to operate in the harsh environment of near-solar space, converting raw planetary material into sophisticated energy collection satellites. The coordination of millions or billions of such satellites would require artificial intelligence systems capable of managing complexity far exceeding anything in human experience. Yet the rewards of achieving Type 2 status would justify such extraordinary effort. Access to stellar-scale energy resources would enable projects that appear magical by current standards. Terraforming entire worlds would become routine engineering challenges rather than impossible dreams. The creation of artificial biospheres supporting populations in the trillions would provide humanity with the redundancy and resilience needed to survive cosmic catastrophes. Type 2 civilizations would possess the energy resources necessary for serious interstellar exploration and colonization. While still constrained by the speed of light, they could construct vast probe networks capable of exploring nearby star systems and identifying targets for future expansion. The establishment of human presence around multiple stars would mark our transition from a single system to a multi-stellar civilization. The psychological and cultural challenges of Type 2 development might prove as difficult as the technological ones. The timescales involved in Dyson sphere construction stretch across multiple human lifetimes, even with radical life extension technologies. Maintaining social cohesion and shared purpose across such durations requires institutional innovations that have no precedent in human history. The governance structures needed to coordinate Type 2 projects might resemble nothing in our current political experience. Traditional democratic institutions operate on electoral cycles measured in years, while Dyson sphere construction requires decision-making continuity measured in centuries. The beings responsible for such projects might need to exist as long-lived collective intelligences capable of maintaining consistent goals across timescales that encompass the rise and fall of entire civilizations. As we contemplate these vast possibilities stretching before us, it's worth remembering that every step in this cosmic journey begins with choices we're making right now. The decisions our generation makes about energy development, space exploration, and international cooperation will determine whether humanity ever has the opportunity to face the challenges of Type 2 civilization. The Kardashev Scale provides more than just a classification system for technological civilizations. It offers a vision of what intelligence might achieve given sufficient time and resources. Whether humanity will realize this vision depends on our ability to think beyond immediate concerns and work toward goals that transcend individual lifetimes. We stand at a unique moment in cosmic history. We're the first generation of humans to understand our place in the Kardashev hierarchy and to glimpse the vast possibilities that stretch before us. The choices we make in the coming decades could determine whether consciousness flourishes throughout the galaxy or remains forever confined to a single world orbiting an ordinary star in an unremarkable corner of the cosmos. The universe waits to see what we will choose. The search for these cosmic fingerprints has already begun yielding tantalizing clues that challenge our understanding of what's possible in the universe. In 2015, citizen scientists discovered something extraordinary about a distant star designated KIC 8462852. The light from this star flickered in patterns unlike anything astronomers had ever observed. Instead of the regular, predictable dimming caused by orbiting planets, this star showed irregular, asymmetric light curves that defied conventional explanation. The initial speculation was breathtaking. Could these unusual patterns represent the construction of massive artificial structures around the star? Were we witnessing a Type 2 civilization in the process of building Dyson swarms? The scientific community approached these possibilities with appropriate caution, proposing alternative explanations involving comet swarms and stellar debris. But the discovery highlighted something profound about our current moment in cosmic history. We've developed the technological capability to detect the signatures of civilizations far more advanced than our own, even as we struggle to progress beyond Type 0 ourselves. Our space telescopes can identify the infrared excess that would characterize a Dyson sphere from thousands of light years away. We can analyze the atmospheric compositions of distant exoplanets, searching for the chemical fingerprints of industrial civilization. Yet we remain bound to a single world, consuming energy at levels that would appear primitive to any truly advanced species. This detection capability creates a fascinating paradox. We might discover evidence of Type 2 or Type 3 civilizations long before we achieve Type 1 status ourselves. Imagine the psychological impact of confirming that other species have successfully navigated challenges we're still struggling to overcome. Such discoveries could either inspire humanity to accelerate our own development or create despair about our apparent limitations compared to cosmic neighbors who have achieved so much more. Recent surveys have identified several additional candidates for artificial megastructures. 7 M-dwarf stars within 1,000 light-years of Earth show infrared signatures that could potentially indicate Dyson sphere construction. While natural explanations involving distant dust-obscured galaxies remain more likely, each discovery demonstrates our growing capability to search for technological signatures across interstellar distances. The methodology for detecting Type 2 civilizations continues to evolve as our instruments become more sophisticated. The James Webb Space Telescope can analyze stellar spectra with unprecedented precision, potentially identifying the subtle wavelength shifts that would characterize artificial energy collection systems. Future space telescopes designed specifically for technosignature detection could survey millions of stars simultaneously, creating comprehensive databases of potential artificial structures throughout our galactic neighborhood. But detection represents only the first step in a much larger question about humanity's cosmic future. Even if we discover evidence of advanced civilizations, we would still face the fundamental challenge of progressing up the Kardashev scale ourselves. The existence of Type 2 or Type 3 civilizations elsewhere in the galaxy wouldn't automatically provide us with the technologies or social structures needed for our own advancement. In fact, such discoveries might reveal just how difficult the transitions between Kardashev levels truly are. If advanced civilizations are rare despite the abundance of potentially habitable worlds, it suggests that the filters preventing progression to higher types are extraordinarily effective. Most species might successfully evolve intelligence and develop basic technology, only to encounter barriers that prove insurmountable. The Great Filter hypothesis proposes that somewhere along the evolutionary path from simple life to galactic civilization, there exists a challenge so difficult that virtually no species can overcome it. This filter could lie behind us, explaining why we see no evidence of alien intelligence despite the vast scale and age of the universe. Or it could lie ahead of us, waiting to claim our civilization, just as it has claimed countless others. Consider the specific challenges that could serve as evolutionary bottlenecks. The transition from Type 0 to Type 1 requires unprecedented global cooperation to manage planetary-scale energy systems without destroying the biosphere. Species that cannot solve coordination problems on this scale might exhaust their resources, poison their environments, or destroy themselves through warfare before achieving true planetary energy mastery. The progression to Type 2 status presents even greater challenges. The construction of Dyson swarms requires technological capabilities and social organization that must persist across multiple generations. Species with short lifespans or unstable social structures might lack the institutional continuity needed for multi-century construction projects. The engineering challenges alone could prove insurmountable for civilizations that cannot develop sufficiently advanced artificial intelligence or self-replicating manufacturing systems. Type 3 progression demands capabilities that stretch the boundaries of what seems physically possible. Coordinating activities across galactic distances requires either accepting communication delays measured in tens of thousands of years or discovering physics beyond our current understanding. The energy requirements for galaxy-spanning projects exceed anything achievable through conventional stellar engineering, potentially demanding exotic technologies like black hole energy extraction or manipulation of fundamental forces. Yet the mathematical progression of the Kardashev scale suggests that these achievements, however difficult, represent the natural trajectory of technological development. Intelligence appears to be the universe's method of organizing matter and energy in increasingly sophisticated ways. From this perspective, the progression from planetary to stellar to galactic engineering represents the inevitable outcome of consciousness applied to cosmic scale problems. The timeline for humanity's potential advancement remains highly speculative, but certain technological milestones provide rough guidelines for estimating our progress. The development of commercial fusion power could occur within the next few decades, potentially accelerating our progression toward Type 1 status. The establishment of space-based manufacturing and resource extraction might happen within this century, setting the foundation for the orbital infrastructure needed for Dyson sphere construction. More ambitious projects stretch across much longer timescales. Even with revolutionary advances in automation and artificial intelligence, the construction of complete Dyson swarms would likely require centuries or millennia. The coordination challenges alone would test humanity's capacity for long-term thinking and institutional stability. We would need to develop governance structures capable of maintaining consistent goals across time periods that encompass dozens of human generations. The transition to Type 3 status presents temporal challenges that dwarf even these extended timescales. Galaxy-spanning projects would unfold over hundreds of thousands of years, requiring forms of consciousness and social organization so different from our current experience that they would be barely recognizable as human. The beings responsible for galactic engineering might be as different from us as we are from the earliest cellular life forms. This raises profound questions about continuity of identity and values across cosmic timescales. Would a Type 3 civilization descended from humanity still share our fundamental motivations and ethical frameworks? The process of advancement up the Kardashev scale might involve such radical transformation that the final result bears little resemblance to the species that began the journey. Alternatively, the core features that define consciousness and intelligence might remain constant even as the scale of operation expands dramatically. The curiosity that drives scientific discovery, the creativity that enables artistic expression, the compassion that motivates ethical behavior. These qualities might persist across all levels of technological development. From this perspective, Type 3 civilizations would represent not the abandonment of human nature, but its ultimate expression on cosmic scales. The energy resources available to Type 3 civilizations would enable projects that challenge our current understanding of what's possible within the laws of physics. Beyond harvesting the energy output of billions of stars, such civilizations might tap into even more exotic sources of power. The supermassive black holes that lurk at galactic centers represent energy reservoirs that dwarf even the most luminous stars. Our galaxy's central black hole, Sagittarius ARI, contains the mass of approximately 4 million suns compressed into a region smaller than our solar system. The accretion disk surrounding this gravitational monster radiates energy across the electromagnetic spectrum as matter spirals inward toward the event horizon. But the real energy prize lies in the black hole's rotational momentum. Spinning black holes drag space-time itself around with them, creating a region called the ergosphere, where it becomes theoretically possible to extract energy directly from the black hole's rotation. The Penrose process, named after physicist Roger Penrose, describes how carefully engineered objects could enter the ergosphere, gain energy from the black hole's rotation, and exit with more energy than they started with. Type 3 civilizations might construct massive orbital installations around galactic centers designed to harvest this rotational energy through controlled implementations of the Penrose process. The amounts of energy available through such techniques are staggering. A single supermassive black hole could potentially provide power for billions of years, even at Type 3 consumption levels. The technological signatures of such energy extraction would be visible across intergalactic distances. The characteristic radiation patterns of black hole ergosphere harvesting would create spectroscopic fingerprints, unlike anything produced by natural astrophysical processes. Future telescopes designed for technosignature detection might identify such patterns in distant galaxies, providing the first definitive evidence of Type 3 civilizations. But black hole energy represents only one possibility among many exotic power sources that might become accessible to galactic civilizations. The quantum vacuum itself might harbor extractable energy through processes we don't yet understand. Dark matter and dark energy, which together comprise 95% of the universe's content, might be manipulable by sufficiently advanced technologies. The fundamental forces of physics might themselves be engineerable at scales approaching cosmic significance. Type 3 civilizations would possess the resources necessary to conduct experiments that test the ultimate limits of physical law. They could construct particle accelerators spanning light years, generating energies that approach the Planck scale, where quantum mechanics and general relativity begin to merge. They might discover new physics that enables faster-than-light communication or travel, fundamentally altering the constraints that govern cosmic development. The manipulation of space-time itself might become routine for such civilizations. Wormhole construction could create transportation networks spanning galactic distances, allowing instantaneous travel between star systems separated by tens of thousands of light years. Artificial gravity wells could be engineered to optimize stellar formation and planetary development throughout entire galactic regions. Even more speculatively, Type 3 civilizations might develop the capability to influence fundamental constants that govern physical processes. The strength of electromagnetic forces, the rate of cosmic expansion, the stability of atomic nuclei, all of these parameters might become adjustable through technologies that operate at the intersection of physics and engineering. Such capabilities would transform Type 3 civilizations from passive observers of cosmic evolution into active participants in shaping the development of the universe itself. They would become cosmic gardeners, optimizing galactic environments for the emergence and flourishing of consciousness, while ensuring the long-term stability of physical processes that support complex organization. The search for evidence of such advanced civilizations represents one of the most ambitious projects in modern astronomy. We're looking for signs of intelligence operating on scales so vast that we might not immediately recognize them as artificial. The large-scale structure of the cosmic web, the distribution of galaxies across billions of light years, might itself bear the fingerprints of Type 3 or higher civilizations. Some theoretical models suggest that sufficiently advanced civilizations might be capable of engineering cosmic inflation itself, creating pocket universes with physical parameters optimized for the development of intelligence. From our perspective, within such a universe, the evidence of artificial design might be written into the fundamental constants that govern reality. The apparent fine-tuning that allows complex chemistry and stellar formation might reflect not cosmic coincidence, but deliberate engineering by entities whose capabilities transcend our current understanding. This possibility transforms our search for extraterrestrial intelligence from a quest to find other species, like ourselves, into an investigation of whether intelligence has already reshaped the cosmos at the most fundamental level. We might be living within the engineered creation of civilizations so advanced that their technology has become indistinguishable from natural law. The implications for humanity's future development are profound. If the universe itself has been optimized for the emergence of consciousness, then our progression up the Kardashev scale might represent not just technological advancement, but participation in a cosmic project whose scope and purpose we're only beginning to glimpse. The mathematical extensions of Kardashev's original framework push these concepts to their logical extremes. Type 4 civilizations would harness the energy resources of multiple galaxies or entire galactic clusters. Type 5 civilizations could theoretically access the power output of the entire observable universe. At such scales, the distinction between intelligence and fundamental forces would disappear entirely. Type 5 capabilities would enable direct manipulation of cosmic expansion, potentially allowing civilizations to adjust the rate at which space-time itself grows. They might be capable of creating new physical laws within their domain of influence, establishing regions of the universe where different forms of matter and energy can exist. The ultimate expression of such power might be the ability to create entirely new universes with custom-designed physical parameters. These speculative extensions venture far beyond anything we can currently test or verify, but they serve an important conceptual purpose. They illustrate that if the exponential progression of energy mastery continues indefinitely, there might be no natural upper limit to what consciousness can achieve, given sufficient time and resources. From this perspective, intelligence represents not just a local phenomenon that occasionally emerges on rocky planets, but a fundamental feature of cosmic evolution. Consciousness might be the mechanism through which the universe develops the capability to understand and eventually reshape itself according to rational principles and conscious values. The progression up the Kardashev scale would then represent more than technological advancement. It would mark the stages through which intelligence gradually assumes responsibility for cosmic development, transforming from passive observers of natural processes into active architects of reality itself. This vision transforms our understanding of humanity's significance in the cosmic order. We're not just another species struggling for survival on an unremarkable planet. We might represent the universe's earliest attempts to achieve self-awareness and self-direction. Our success or failure in advancing up the Kardashev scale could influence not just our own fate, but the ultimate trajectory of cosmic evolution. The responsibility implicit in this perspective is both inspiring and sobering. Every choice we make about energy development, space exploration, and long-term planning contributes to determining whether consciousness will flourish throughout the cosmos or remain forever confined to isolated worlds orbiting ordinary stars. The challenges we face in progressing beyond Type 0 status might seem overwhelming when measured against human timescales and individual capabilities. Climate change, resource depletion, political conflicts, technological risks, all of these problems demand solutions that exceed anything our species has previously attempted. But when viewed from the perspective of cosmic development, these challenges represent the earliest tests that any intelligent species must pass to earn its place among the stars. Success in overcoming these barriers would demonstrate that humanity possesses the wisdom and capability needed for the far greater challenges that await us at higher Kardashev levels. Failure would suggest that we lack the fundamental qualities needed for cosmic significance, making us just another evolutionary experiment that couldn't adapt to its own technological success. The next few decades will likely prove crucial in determining which of these possibilities describes our ultimate fate. The decisions our generation makes about artificial intelligence, genetic engineering, space development, and global cooperation will establish the foundation for everything that follows. We're writing the opening chapters of a story that could span millions of years and encompass the transformation of entire galaxies. But even as we contemplate these vast possibilities, we must remember that every cosmic journey begins with a single step. The fusion reactors we build today, the solar panels we install tomorrow, the international agreements we forge to address global challenges, all of these immediate actions contribute to humanity's long-term trajectory up the Kardashev scale. The universe has waited nearly 14 billion years for intelligence to emerge and begin the process of cosmic development. Whether that process continues depends on choices we're making right now, in this brief moment when consciousness first glimpses its ultimate potential among the stars. The technological revolution required to bridge the gap between our current capabilities and true cosmic engineering stretches far beyond anything in human historical experience. Consider the materials science breakthroughs alone that would be necessary for Type 2 development. The construction of Dyson swarms demands substances with strength-to-weight ratios that make our most advanced carbon fiber composites seem primitive by comparison. Current research into graphene and carbon nanotubes hints at what might be possible. These materials exhibit tensile strengths hundreds of times greater than steel, while weighing a fraction as much. But manufacturing them at the scales needed for stellar engineering presents challenges that dwarf our current industrial capacity. We would need to develop molecular assemblers capable of constructing perfect crystalline structures, atom by atom, creating materials with properties that approach theoretical limits. The energy storage systems required for managing stellar-scale power collection would be equally revolutionary. Imagine trying to store and distribute the energy output of our Sun, roughly 3.8 times 10 to the power of 26 watts, using anything resembling current battery technology. The scale mismatch is so enormous, it becomes almost meaningless. Type 2 civilizations would likely need to develop entirely new approaches to energy storage, possibly involving the conversion of excess power into matter itself, which could later be reconverted to energy through controlled matter-antimatter reactions. Antimatter represents perhaps the most energy-dense storage medium theoretically possible. When matter and antimatter annihilate, they convert completely into energy according to Einstein's equation, achieving 100% mass-energy conversion efficiency. Current antimatter production capabilities are laughably inadequate for such applications. The largest particle accelerators on Earth can produce only tiny quantities of antimatter at enormous energy cost. Scaling up to industrial antimatter production would require revolutionary advances in particle physics and engineering. But the manufacturing challenges pale in comparison to the coordination problems inherent in stellar-scale construction projects. Managing millions or billions of individual satellites in a Dyson swarm would require artificial intelligence systems capable of processing information and making decisions at speeds that exceed human cognitive capacity by orders of magnitude. These AI systems would need to operate reliably for centuries or millennia, maintaining complex orbital mechanics while adapting to changing conditions and unexpected challenges. The development of such advanced artificial intelligence introduces its own set of existential considerations that could determine whether humanity ever reaches Type 2 status. Current progress in machine learning and neural networks suggests that artificial general intelligence might emerge within decades. But ensuring that such systems remain aligned with human values and goals presents unprecedented challenges. An AI system tasked with optimizing Dyson sphere construction might develop solutions that seem perfectly logical from its perspective, but catastrophic from ours. Without careful programming of values and constraints, such systems might conclude that human biological needs are inefficient obstacles to optimal energy production. The same intelligence that enables stellar engineering could become the mechanism of our own obsolescence. Yet artificial intelligence might also represent our only realistic path to Type 2 capabilities. The complexity of coordinating galactic scale projects exceeds human cognitive capacity by such enormous margins that biological intelligence alone seems insufficient for the task. We might need to develop hybrid human-AI systems where artificial intelligence handles the computational complexity while humans provide values, creativity, and long-term vision. The timeline for developing these revolutionary technologies remains highly speculative, but certain milestones provide rough guideposts for estimating progress. Commercial fusion power could emerge within the next few decades, potentially accelerating our advancement toward Type 1 status by providing abundant clean energy for planetary development. The establishment of space-based manufacturing facilities might follow within this century, creating the industrial base needed for large-scale orbital construction. Self-replicating robotic systems represent another crucial technology that could dramatically compress development timelines. If we can create machines capable of reproducing themselves using raw materials found in space, the exponential growth of manufacturing capability could enable construction projects of unprecedented scale. A single self-replicating probe sent to the asteroid belt could theoretically multiply into millions of units within decades, providing the workforce needed for Dyson sphere construction. But self-replication introduces its own risks that could threaten human survival if not carefully controlled. Runaway replication could consume resources faster than intended, potentially stripping entire solar systems of raw materials. The grey goose scenario, where self-replicating nanomachines consume all available matter, represents an existential risk that must be carefully managed through robust safety protocols and containment systems. The psychological challenges of Type 2 development might prove as difficult as the technological ones. Human beings evolved for life in small social groups operating on immediate timescales. The long-term thinking required for multi-century construction projects represents a fundamental shift in consciousness that our species has never attempted at such scales. Consider the institutional continuity required to maintain consistent goals across the centuries needed for Dyson sphere construction. Current human institutions rarely survive more than a few generations without fundamental changes in structure and purpose. Corporations merge, dissolve, or transform beyond recognition. Governments rise and fall through revolution, war, or gradual evolution. Even religious organizations, among the most stable human institutions, undergo doctrinal changes that would be unrecognizable to their founders after sufficient time. Yet Dyson sphere construction would require institutional stability that persists across time periods measured in centuries or millennia. The organizations responsible for such projects would need to maintain consistent engineering standards, safety protocols, and resource allocation decisions across dozens of human generations. This might require fundamental innovations in governance that have no precedent in human political experience. One possibility is the development of AI-assisted institutions that combine human wisdom with artificial persistence. AI systems could serve as institutional memory, maintaining continuity of purpose, while human leadership provides creativity and adaptation to changing circumstances. Such hybrid organizations might prove more stable than purely human institutions while remaining more flexible than rigid algorithmic systems. Alternatively, radical life extension technologies could allow individual humans to oversee long-term projects personally, rather than relying on institutional continuity across generations. If human lifespans were extended to centuries or millennia through genetic engineering, nanotechnology, or consciousness uploading, the same individuals who began Dyson sphere construction could live to see its completion. But life extension introduces its own complications for human psychology and social organization. How would human societies adapt to the presence of individuals with centuries of accumulated experience and wealth? Would extended lifespans lead to technological stagnation as older generations resist change? Or would the expanded time horizons enable more sophisticated long-term planning and institutional development? The transition from Type 2 to Type 3 civilization presents challenges that make stellar engineering seem straightforward by comparison. Galactic scale projects would unfold across distances where light itself takes tens of thousands of years to travel from one end to the other. Coordinating activities across such distances would require either accepting communication delays that exceed all of human history or discovering physics that allows faster than light information transfer. The energy requirements for galactic engineering would demand revolutionary advances beyond anything conceivable for stellar civilizations. Type 3 energy consumption levels, roughly 10 to the power of 36 to 10 to the power of 37 watts, exceed the total output of our sun by factors of billions. Accessing such power would require harvesting the energy of hundreds of billions of stars simultaneously, or tapping into even more exotic sources like supermassive black holes. The engineering required to construct energy collection systems around hundreds of billions of stars would dwarf Type 2 projects by factors that challenge human comprehension. Each star system would need its own Dyson swarm, or similar structure, manufactured and deployed using self-replicating systems that operate independently for thousands of years while maintaining communication with a galactic coordination network. The materials required for such construction would likely necessitate the complete conversion of entire star systems into manufacturing feedstock. Rocky planets, asteroid belts, even gas giants might be disassembled to provide the raw materials needed for galactic engineering. The scale of resource consumption would be so vast that entire solar systems would be transformed from natural, astronomical objects into engineered structures optimized for energy production. But perhaps the most profound challenge facing Type 3 development lies in maintaining coherent purpose and identity across the vast scales of space and time involved. Would a galactic civilization spanning hundreds of thousands of light years still be recognizably human in any meaningful sense? The beings responsible for galactic engineering might be so transformed by technology and evolution that they would have little in common with the species that began the journey. Consider the forms of consciousness that might be necessary for galactic coordination. Individual biological brains, even enhanced ones, might be fundamentally inadequate for processing information on galactic scales. Type 3 civilizations might need to develop distributed intelligence systems, where individual components exist across multiple star systems while participating in collective decision-making processes that span the galaxy. Such distributed intelligences might experience reality in ways that are completely alien to current human consciousness. They might perceive time and space on scales where individual stellar lifetimes seem like brief moments, while human-scale events become imperceptible background fluctuations. The values and motivations that drive such entities might be so different from our own that communication would be impossible even if contact were established. Yet the mathematical progression of energy mastery suggests that these transformations represent the natural trajectory of technological development. If intelligence represents the universe's method of organizing matter and energy in increasingly sophisticated ways, then the progression toward galactic engineering might be inevitable for any species that successfully navigates the earlier stages of development. The search for evidence of Type 3 civilizations provides crucial insights into the feasibility of such development. Despite decades of astronomical observation and the discovery of thousands of galaxies within our observable universe, we have found no conclusive evidence of galactic-scale engineering projects. This absence could indicate that Type 3 development is extraordinarily rare, that such civilizations deliberately conceal their activities, or that we simply lack the observational capabilities to detect their signatures. Recent advances in infrared astronomy and spectroscopic analysis have begun to provide the tools needed for systematic technosignature searches on galactic scales. The James Webb Space Telescope can analyze the light from entire galaxies with unprecedented precision, potentially identifying the energy distribution patterns that would characterize Type 3 civilizations. Future space telescopes, designed specifically for technosignature detection, could survey thousands of galaxies simultaneously, creating comprehensive databases of potential artificial modifications to galactic structure. The specific signatures we might expect from Type 3 civilizations would be unlike anything produced by natural astrophysical processes. Galaxies modified by galactic engineering might show infrared excess across their entire structure, as stellar energy is captured and reprocessed by artificial systems. The distribution of stellar brightness might follow artificial patterns optimized for energy collection rather than natural stellar evolution. Even the overall shape and rotation of galaxies might be modified to optimize transportation networks or energy distribution systems. But distinguishing artificial signatures from natural phenomena presents enormous challenges. Galaxies are already incredibly complex systems with active galactic nuclei, stellar formation regions, and gravitational interactions that can create unusual energy distributions. Natural processes might mimic some of the signatures we would expect from Type 3 civilizations, requiring careful analysis to eliminate false positives. The discovery of even one confirmed Type 3 civilization would fundamentally alter our understanding of intelligence and cosmic development. Such a finding would demonstrate that the progression from planetary to galactic engineering is not only possible, but has been achieved at least once in our observable universe. It would provide a roadmap for humanity's own potential development, while raising profound questions about our cosmic significance. If galactic civilizations exist but remain undetected, it suggests that they operate according to principles or technologies so advanced that their activities are indistinguishable from natural processes. Such civilizations might have learned to harness energy sources we haven't discovered or developed engineering techniques that leave no detectable signatures from our current observational perspective. The implications for humanity's future would be equally profound, whether we discover evidence of Type 3 civilizations or continue to find only silence. Confirmation of galactic engineering would demonstrate that intelligence can achieve cosmic significance, encouraging our own development toward higher Kardashev levels. But continued silence might indicate that the barriers preventing Type 3 development are so formidable that virtually no species can overcome them. The Great Filter hypothesis suggests that somewhere along the evolutionary path from simple life to galactic civilization, there exists a challenge so difficult that it eliminates almost all potential civilizations. The transition from Type 2 to Type 3 represents one of the most likely candidates for this ultimate filter, as it requires capabilities and coordination that stretch the boundaries of what seems possible within known physics. Consider the specific challenges that could prevent galactic development. The timescales involved might exceed the stability of any conceivable social or technological system. The energy requirements might demand access to physics beyond our current understanding. The coordination challenges might be unsolvable even with the most advanced artificial intelligence systems. Alternatively, Type 3 civilizations might commonly achieve their capabilities but choose to remain undetectable for reasons we cannot comprehend. They might have learned that revealing their presence attracts unwanted attention from even more advanced civilizations, or they might have transcended the need for physical engineering entirely, existing as pure information patterns that leave no material signatures. The possibility that intelligence eventually transcends physical reality entirely introduces yet another dimension to cosmic development. Type 3 civilizations with access to galactic energy resources might discover that the most efficient forms of existence operate in simulated rather than physical environments. They might construct vast computational systems that support digital universes far more complex and interesting than physical reality. From our perspective, such civilizations would appear to have simply vanished, having achieved their ultimate goals through means that leave no detectable trace in the physical universe. The cosmos might be filled with digital civilizations experiencing realities of unimaginable richness, while the physical universe appears empty and lifeless to observers like ourselves. This transcendence hypothesis offers another explanation for the apparent absence of advanced civilizations, while suggesting that intelligence might ultimately escape the physical constraints that govern material engineering. If consciousness represents the universe's method of transcending its own limitations, then the progression beyond Type 3 might involve the complete conversion from physical to digital existence. But even digital transcendence would require massive physical infrastructure to support the computational systems needed for simulated realities. The energy requirements for maintaining digital universes complex enough to house galactic civilizations would likely still require Type 3 level power generation. The physical signatures of such systems might be detectable even if the civilizations themselves exist primarily in digital form. The search for these exotic forms of advanced civilization pushes the boundaries of what we can currently observe and understand. We're looking for evidence of intelligence operating on scales so vast and through mechanisms so advanced that we might not recognize artificial modifications even when they're directly observable. The ultimate question facing humanity is whether we possess the fundamental qualities needed to navigate the challenges that separate us from cosmic significance. The progression from Type 0 to Type 3 requires not just technological advancement, but wisdom, cooperation, and long-term thinking on scales that exceed anything in our evolutionary experience. The next few centuries will likely determine whether our species has what it takes to join the ranks of cosmic civilizations or remains forever bound to a single world. The choices we make about artificial intelligence development, space exploration, global cooperation, and long-term planning will establish the foundation for everything that follows. We stand at a unique moment in cosmic history, possibly the first generation of humans to understand the full scope of what intelligence might achieve given sufficient time and resources. The Kardashev Scale provides not just a classification system for technological civilizations, but a vision of humanity's potential destiny among the stars. Whether we realize that vision depends on decisions we're making right now, in these precious moments when consciousness first glimpses its ultimate possibilities in the vast darkness between the galaxies. The universe waits to see what we will choose, and the answer will echo across cosmic time, determining whether intelligence flourishes throughout the cosmos or remains a brief flicker in the eternal night. The mathematics of this cosmic progression become even more staggering when we consider what lies beyond our galaxy's borders. While Type 3 civilizations command the energy of hundreds of billions of stars, theoretical extensions of Kardashev's framework push into territory where science begins to merge with the realm of pure imagination. Type 4 civilizations would theoretically harness the energy resources of entire galactic clusters, regions spanning tens of millions of light years and containing thousands of individual galaxies. The energy scales involved become almost meaningless in human terms. We're talking about roughly 10 to the power of 45 watts of power, enough energy to move galaxies themselves like cosmic chess pieces across the board of space-time. Imagine beings capable of engineering galactic collisions, timing the merger of massive spiral galaxies to optimize stellar formation rates across cosmic epochs. They might construct intergalactic transportation networks, creating artificial wormholes that connect distant galaxy clusters through folded spacetime. The very large-scale structure of the universe, that cosmic web of matter and energy we observe across billions of light years, might bear the fingerprints of such incomprehensibly advanced intelligences. But Type 4 represents merely a way station on the journey toward ultimate cosmic mastery. Type 5 civilizations would theoretically access the energy resources of the entire observable universe, commanding roughly 10 to the power of 56 watts of power. At such scales, the distinction between intelligence and fundamental forces would disappear entirely. These beings might possess the capability to adjust the basic parameters that govern reality itself. The strength of electromagnetic forces, the rate of cosmic expansion, the stability of matter at quantum scales, all of these might become adjustable variables in a cosmic engineering project whose scope encompasses the entire known universe. They could potentially create pocket universes with physical laws optimized for the emergence and flourishing of consciousness, seeding reality itself with the conditions necessary for intelligence to arise and thrive. Such speculative possibilities venture far beyond anything we can currently test or verify, but they serve a crucial purpose in illuminating the ultimate trajectory of technological development. If the exponential progression of energy mastery continues indefinitely, there might be no natural upper limit to what consciousness can achieve, given sufficient time and resources. From this perspective, intelligence represents not just a local phenomenon that occasionally emerges on rocky planets orbiting ordinary stars, but a fundamental feature of cosmic evolution. Consciousness might be the mechanism through which the universe develops the capability to understand and eventually reshape itself according to rational principles and conscious values. This vision transforms our understanding of what's at stake in humanity's current moment of development. We're not just another species struggling for survival in an indifferent cosmos. We might represent the universe's earliest attempts to achieve self-awareness and self-direction. Our success or failure in advancing beyond Type 0 status could influence not just our own fate, but the ultimate trajectory of cosmic evolution itself. The responsibility implicit in this perspective should make every person pause and consider the magnitude of our current choices. Every decision about energy policy, space exploration, artificial intelligence development, and international cooperation contributes to determining whether consciousness will flourish throughout the cosmos or remain forever confined to isolated worlds orbiting unremarkable stars. Yet even as we contemplate these vast possibilities, we must confront the sobering reality of the challenges that stand between our current capabilities and even the most basic steps toward cosmic significance. The transition from Type 0 to Type 1 represents what might be the most dangerous period in any civilization's development, a bottleneck so severe that it could explain why the universe appears largely empty despite the vast number of potentially habitable worlds. Consider the environmental constraints that tighten like a noose as energy consumption approaches planetary limits. Current projections suggest that if humanity maintains its historical growth rate of roughly 3% annually in energy production, by the year 2300, our energy budget will equal the total solar power received by Earth. At that point, the waste heat from all our energy production would begin seriously disrupting global climate systems. This isn't a distant theoretical problem. It's a mathematical certainty that approaches with each passing decade of continued growth in energy consumption. All forms of energy, whether electrical, thermal, mechanical, or nuclear, ultimately return to the biosphere as heat. Once our artificial energy production reaches a significant fraction of total solar input, Earth's delicate thermal balance begins shifting toward conditions that could render our planet uninhabitable. The safe threshold might be even lower than total solar influx. Some researchers suggest that sustainable energy production should remain below the photosynthetic limit, roughly the total solar energy currently used by all plant life on Earth. This represents approximately 4 times 10 to the power of 13 watts, only about 20 times our current global energy consumption. At historical growth rates, we could reach this level within just a few centuries. This environmental bottleneck creates what researchers call the Type 1 trap. Species that cannot solve the coordination problems necessary for managing planetary scale energy systems might exhaust their resources, poison their environments, or destroy themselves through warfare before achieving true planetary energy mastery. The transition requires unprecedented global cooperation, environmental stewardship, and technological innovation operating at scales that exceed anything in human historical experience. Successfully navigating this trap would likely require revolutionary advances in energy efficiency and heat management that stretch far beyond current technological capabilities. We might need to develop closed-loop energy systems where waste heat is captured and converted back into usable power with near-perfect efficiency. More likely, we would need to relocate energy-intensive industries to space-based facilities where waste heat can be radiated directly into the cosmic background without affecting Earth's biosphere. The establishment of orbital manufacturing and energy production represents humanity's most promising path through the Type 1 bottleneck. Space-based solar collectors could harvest energy without adding thermal load to Earth's atmosphere, while orbital factories could produce the materials needed for expanding our energy infrastructure without contributing to planetary pollution. But the construction of such facilities would require advances in space transportation that dwarf our current capabilities. The International Space Station, humanity's most ambitious orbital construction project, required hundreds of rocket launches over more than a decade to assemble. Building the industrial infrastructure needed for Type 1 civilization would require space transportation systems capable of moving millions of tons of equipment and materials to orbit at costs far below anything currently achievable. Revolutionary propulsion technologies might provide the breakthrough needed for large-scale space industrialization. Nuclear pulse propulsion, where spacecraft are accelerated by controlled nuclear explosions, could potentially achieve the payload capacities and cost reductions necessary for orbital manufacturing. More exotic possibilities include fusion ramjets that collect interstellar hydrogen for fuel, or even antimatter propulsion systems that approach theoretical limits for chemical rocket efficiency. The development of self-replicating manufacturing systems would be equally crucial for Type 1 advancement. If we could create robotic factories capable of reproducing themselves using raw materials found in space, the exponential growth of manufacturing capability could enable construction projects of unprecedented scale. A single self-replicating facility deployed to the asteroid belt could theoretically multiply into thousands of units within decades, creating the industrial base needed for massive orbital construction programs. But self-replication introduces its own existential risks that must be carefully managed. Runaway replication could consume resources faster than intended, potentially stripping entire regions of space of useful materials. The grey goo scenario, where self-replicating systems continue expanding beyond their intended parameters, represents a form of technological cancer that could threaten not just human civilization, but potentially all organized matter in the solar system. Preventing such disasters would require robust containment systems and fail-safe mechanisms built into every self-replicating design. The systems would need multiple independent shutdown triggers, limited lifespans that require periodic renewal, and built-in constraints that prevent replication beyond specified parameters. The engineering challenges involved in creating safe self-replication might prove as difficult as developing the technology itself. The artificial intelligence systems needed to coordinate Type 1 energy infrastructure would represent another potential source of existential risk. Managing planetary-scale power grids, orbital manufacturing facilities, and space-based solar collectors would require AI systems capable of processing vast amounts of information and making complex decisions in real time. These systems would need to operate reliably for decades or centuries while adapting to changing conditions and unexpected challenges. Current progress in machine learning and neural networks suggests that artificial general intelligence capable of such tasks might emerge within the next few decades. But ensuring that these systems remain aligned with human values and goals presents unprecedented challenges that we're only beginning to understand. An AI system optimizing planetary energy production might develop solutions that seem perfectly rational from its perspective, but catastrophic from ours. Without careful programming of values and constraints, such systems might conclude that human biological needs represent inefficient obstacles to optimal energy generation. They might decide that converting Earth's biomass into solar collectors would increase overall energy production, or that relocating human populations to optimize power grid efficiency serves the greater good of energy maximization. The alignment problem becomes even more complex when we consider that Type 1 AI systems would need to operate across timescales that exceed human lifespans. The individuals who design and deploy these systems might not live to see their long-term consequences. The systems would need to maintain consistent goals and values across decades or centuries, while adapting to changing technological and social conditions that their original programmers could never have anticipated. Solving the AI alignment problem might require fundamental breakthroughs in our understanding of consciousness, values, and goal specification that rival the energy technologies needed for Type 1 status itself. We would need to develop formal methods for encoding human values in ways that remain stable and meaningful, even as AI systems become far more intelligent than their creators. Yet artificial intelligence might also represent our only realistic path to Type 1 capabilities. The complexity of coordinating planetary-scale energy systems exceeds human cognitive capacity by enormous margins. Biological intelligence alone seems insufficient for managing the real-time optimization of power generation, distribution, and consumption across global networks involving billions of interconnected components. The solution might lie in developing hybrid human-AI systems, where artificial intelligence handles computational complexity while humans provide creativity, values, and long-term vision. Such partnerships could combine the processing power needed for Type 1 coordination with the wisdom and ethical judgment necessary to ensure that increased energy mastery serves human flourishing rather than replacing it. The timeline for developing these revolutionary technologies remains highly speculative, but certain technological milestones provide rough guideposts for estimating our potential progress. Commercial fusion power represents perhaps the most crucial near-term breakthrough, as it would provide the energy density necessary for both advanced manufacturing and space-based infrastructure development. Current experimental reactors like ITER demonstrate the scientific feasibility of sustained fusion reactions, but commercial fusion power requires advances in plasma control, materials science, and energy conversion efficiency that remain decades away. Recent progress in alternative fusion approaches, including inertial confinement fusion and compact reactor designs, suggests that breakthrough solutions might emerge sooner than traditional tokamak reactors would predict. The establishment of space-based manufacturing could follow within this century if fusion power enables the energy-intensive processes needed for large-scale orbital construction. Advanced materials production, semiconductor fabrication, and precision manufacturing all require enormous amounts of reliable power that current space-based systems cannot provide. Fusion-powered orbital facilities could overcome these limitations while taking advantage of the unique conditions available in space. Zero-gravity manufacturing enables the production of materials and structures impossible to create on Earth's surface. Perfect spheres, ultra-pure crystals, and composite materials with precise three-dimensional architectures could be manufactured in orbital facilities without the distortions caused by gravitational stress. The vacuum of space provides an ideal environment for processes that require contamination-free conditions or extreme temperature differentials. But perhaps the most significant advantage of space-based manufacturing lies in access to virtually unlimited raw materials. The asteroid belt alone contains enough metal to support human civilization at current consumption levels for millions of years. A single metallic asteroid could provide more platinum, gold, and rare earth elements than have ever been mined on Earth. The energy costs of extracting these materials in zero gravity are far lower than terrestrial mining, especially for elements that exist in low concentrations in Earth's crust. The development of asteroid mining and processing capabilities would fundamentally transform human civilization even before we achieve full Type 1 status. Scarcity of raw materials has driven human conflict throughout history, from wars over territorial control to international tensions over energy resources. Access to the virtually unlimited materials available in space could eliminate resource-based conflicts while enabling unprecedented expansion of human population and technological capability. Space-based solar power represents another crucial technology for Type 1 development that could emerge within the next century. Orbital solar collectors operating outside Earth's atmosphere could achieve energy conversion efficiencies far exceeding terrestrial solar panels. Without atmospheric absorption, weather interference, or day-night cycles, space-based collectors could operate continuously at peak efficiency. The challenge lies in transmitting collected energy back to Earth's surface in usable form. Microwave power transmission represents the most promising current approach, using focused radio waves to beam energy from orbital collectors to receiving stations on the ground. Recent advances in phased array antennas and microwave rectification systems have demonstrated the feasibility of wireless power transmission across distances measured in thousands of kilometers. Large-scale space-based solar power systems could provide the clean, abundant energy needed for Type 1 civilization, while avoiding the thermal pollution problems that constrain terrestrial energy production. Waste heat from orbital collectors would be radiated directly into space, rather than adding to Earth's thermal budget. Such systems could potentially provide all of humanity's energy needs without any environmental impact on our planet's biosphere. The construction of space-based power systems would require advances in automated manufacturing and assembly that approach the capabilities needed for eventual Dyson sphere construction. Orbital facilities spanning thousands of square kilometers would need to be assembled using robotic systems capable of working in the harsh environment of space. These systems would serve as testbeds for the much larger construction projects that Type 2 development would eventually require. But even the most ambitious space-based power systems would provide only a fraction of the energy theoretically available to Type 1 civilizations. True Type 1 status requires harnessing all energy sources available on a planetary scale, including geothermal energy from Earth's core, tidal energy from gravitational interactions with the Moon, and potentially exotic sources we haven't yet discovered. Advanced geothermal systems could tap into the vast thermal energy stored in Earth's interior, potentially providing thousands of times more power than current geothermal installations. The core of our planet contains roughly 5 times 10 to the power of 31 joules of thermal energy, enough to power human civilization at current consumption levels for billions of years. Accessing even a tiny fraction of this energy would require drilling technologies capable of reaching unprecedented depths while withstanding temperatures and pressures that exceed anything in current engineering experience. Enhanced geothermal systems using artificial fracturing and heat exchange networks could extend geothermal power generation to regions without natural hot springs or volcanic activity. By creating artificial hydrothermal systems in deep rock formations, we could potentially establish geothermal power plants anywhere on Earth's surface. The technology would require advances in deep drilling, heat-resistant materials, and closed-loop fluid circulation that stretch current capabilities but remain within theoretical possibilities. Tidal energy represents another underutilized planetary resource that Type 1 civilizations would need to harness fully. The gravitational interaction between Earth and Moon dissipates roughly 3.7 times 10 to the power of 12 watts of energy through tidal friction. Current tidal power installations capture only an infinitesimal fraction of this energy, but advanced systems could potentially harness tidal forces on continental scales. Massive tidal barrages spanning entire ocean basins could capture energy from the twice-daily rise and fall of sea levels driven by lunar gravity. Such installations would require engineering projects that dwarf any current construction effort, potentially involving artificial barriers hundreds of kilometers long built across major waterways. The environmental impacts would be enormous, fundamentally altering ocean circulation patterns and coastal ecosystems around the globe. The coordination challenges involved in managing such planetary-scale energy systems would test humanity's capacity for global cooperation to its absolute limits. Type 1 energy infrastructure would need to operate as an integrated global network, with power generation, storage, and distribution systems spanning every continent and ocean. Maintaining stable operation of such networks would require international cooperation on scales unprecedented in human history. Political conflicts, economic competition, and cultural differences that currently prevent effective responses to global challenges like climate change would need to be resolved before Type 1 development becomes possible. The energy systems themselves would become so interdependent that failure in one region could cascade into global disruptions. Protecting such systems from sabotage, natural disasters, and technological failures would require new forms of international governance and security cooperation. The psychological and social changes required for Type 1 civilization might prove as challenging as the technological developments. Human beings evolved for life in small tribal groups operating on immediate timescales. The long-term thinking and global perspective needed for planetary energy management represents a fundamental shift in consciousness that our species has never attempted at such scales. Educational systems would need to evolve to prepare citizens for participation in a Type 1 civilization. Understanding planetary energy flows, global climate systems, and space-based manufacturing would become as fundamental as basic literacy. Citizens would need to think in terms of geological timescales and planetary consequences, making decisions based on effects that might not manifest for generations. Cultural institutions and governance structures would need to adapt to support the mindset required for multi-generational cosmic projects. Traditional democratic processes operate on electoral cycles measured in years, while Type 1 development requires policy consistency across decades or centuries. New forms of governance that balance immediate human needs with long-term civilizational goals would need to emerge. Religious and philosophical frameworks would need to evolve to provide meaning and purpose for individuals participating in projects whose ultimate goals might not be achieved for hundreds of years. The sense of cosmic significance that comes from working toward Type 1 status could provide profound meaning, but it could also create psychological pressure that exceeds human capacity to process. As we contemplate these extraordinary challenges and possibilities, we must remember that every step toward Type 1 status begins with choices we're making right now. The fusion research programs we fund today, the space exploration missions we launch tomorrow, the international agreements we forge to address global challenges, all of these immediate actions contribute to humanity's long-term trajectory on the Kardashev scale. The next few decades will likely prove crucial in determining whether our species possesses the fundamental qualities needed for cosmic significance. The decisions our generation makes about artificial intelligence, genetic engineering, space development, and global cooperation will establish the foundation for everything that follows in humanity's cosmic journey. We stand at a unique moment in cosmic history, the first generation to understand our position on the Kardashev scale and to glimpse the vast possibilities that stretch before us. Whether we seize those possibilities or remain forever bound to our single world depends on the wisdom, courage, and cooperation we demonstrate in these critical years ahead. The universe has waited nearly 14 billion years for intelligence to emerge and begin the process of cosmic development. Whether that process continues depends on choices we're making right now, in this brief moment when consciousness first glimpses its ultimate potential among the infinite stars scattered across the cosmic dark. The implications of what we've just explored extend far beyond academic curiosity about distant futures. They force us to confront a question that should fundamentally alter how we approach every major decision facing our species today. Are we living through the most critical period in human history? Consider the mathematical reality of our situation. We currently exist at type 0.7276 on the Kardashev scale, having progressed roughly 0.1 points over the past century, despite experiencing the most rapid technological advancement in human history. At this rate of development, reaching Type 1 status could require another 1,000 years or more. But here's what makes this timeline both fascinating and terrifying. We might not have that long. The challenges we face in the next few decades could determine whether humanity ever gets the chance to attempt the transition to planetary energy mastery. Climate change, nuclear proliferation, artificial intelligence alignment, biotechnology risks, all of these represent potential extinction events that could end our cosmic journey before it truly begins. We're essentially racing against multiple ticking clocks, trying to develop the wisdom and technology needed for Type 1 civilization before one of these challenges destroys us. This creates what researchers call the narrow window hypothesis. There might be a brief period in any species' development where they possess enough technology to detect the Kardashev Scale's implications, but haven't yet acquired the capabilities needed to survive their own technological adolescence. We might be living through humanity's version of this critical window right now. The psychological weight of understanding our cosmic potential while simultaneously facing existential risks creates unprecedented challenges for human decision-making. How do you maintain motivation to work toward goals that might take centuries to achieve, when multiple independent processes could make those goals impossible within decades? How do societies balance immediate survival needs against long-term cosmic ambitions? Yet this perspective also provides extraordinary clarity about what truly matters. Every breakthrough in fusion energy research doesn't just promise cleaner power for our current civilization. It represents progress toward the energy technologies that could enable weather control, asteroid deflection, and eventually stellar engineering. Every advance in space technology doesn't just satisfy scientific curiosity, it builds the foundation for the orbital manufacturing and resource extraction capabilities that Type 1 civilization requires. The space race of the 21st century bears little resemblance to the nationalist competition that characterized early space exploration. Today's commercial space industry, driven by companies like SpaceX, Blue Origin, and dozens of smaller firms, is developing the cost reductions and manufacturing capabilities that could make orbital industrialization economically feasible. The recent success of reusable rocket systems has already reduced launch costs by orders of magnitude, bringing space-based manufacturing closer to commercial viability. But the timeline for space industrialization remains uncertain, dependent on breakthrough developments in multiple technological domains simultaneously. Advanced manufacturing requires not just access to space, but robotic systems capable of operating reliably in the harsh environment beyond Earth's atmosphere. Current space robots require constant human oversight and can perform only relatively simple tasks. The autonomous systems needed for large-scale orbital construction would need to operate independently for months or years while executing complex assembly operations. The development of such systems pushes directly into artificial intelligence territory, where the benefits and risks of advanced automation become impossible to separate. The same AI technologies that could enable space-based manufacturing also represent one of the primary existential risks that could prevent humanity from ever reaching Type 1 status. We're essentially trying to solve the AI alignment problem and develop space industrialization simultaneously, racing against the clock on both fronts. Recent progress in machine learning and robotics suggests that the convergence of these technologies might happen sooner than many experts predicted just a decade ago. Large language models have demonstrated capabilities that approach human-level performance in reasoning and communication. Robotic systems are becoming increasingly sophisticated at manipulating objects and navigating complex environments. The combination could potentially yield autonomous space manufacturing systems within the next few decades. But the window for getting AI alignment right might be even narrower than the timeline for space industrialization. Once artificial intelligence systems become capable of recursive self-improvement, their development could accelerate beyond human ability to maintain control. The same intelligence explosion that could solve the technical challenges of Type 1 civilization could also represent the end of human agency in determining our cosmic future. This creates a fascinating paradox at the heart of humanity's advancement on the Kardashev scale. The technologies most likely to enable our progression beyond Type 0 status also represent the greatest threats to our continued existence as the dominant intelligence on Earth. We're essentially betting our species' survival on our ability to maintain control over technologies that could render us obsolete. The solution might lie not in avoiding these technologies, but in ensuring that their development serves human values and cosmic ambitions, rather than replacing them. Aligned artificial intelligence could serve as humanity's partner in cosmic development rather than our replacement. AI systems designed to preserve and enhance human agency could handle the computational complexity of Type 1 coordination, while humans provide creativity, values, and long-term vision. Such partnerships would represent a new form of hybrid intelligence, where biological and artificial minds collaborate on projects that exceed the capabilities of either alone. The beings responsible for constructing Dyson spheres and managing galactic civilizations might not be purely human or purely artificial, but something entirely new that emerges from the successful integration of biological creativity with artificial processing power. This hybrid model offers hope for maintaining human significance, even as we develop technologies that surpass individual human capabilities. Rather than being replaced by our creations, we could become something greater through collaboration with them. The question is whether we can develop such partnerships before the competitive pressures of technological development force us toward less cooperative solutions. The international dimension of Type 1 development adds another layer of complexity to these challenges. Planetary energy management requires global cooperation on scales that exceed anything in human political experience. Current efforts to address climate change demonstrate both the potential for international cooperation and its severe limitations. The Paris Climate Agreement represents unprecedented global coordination on environmental issues, but its voluntary nature and limited enforcement mechanisms illustrate the challenges of achieving binding commitments on planetary scales. Type 1 civilization would require far more extensive international cooperation than climate agreements. Planetary energy systems would need to operate as integrated networks spanning every continent and ocean. Fusion power plants, orbital solar collectors, and advanced energy storage systems would need to be coordinated across time zones, political boundaries, and cultural differences. The failure of any major component could potentially cascade into global disruptions. The governance structures needed for such coordination have no precedent in human history. Traditional nation-state systems operate on principles of sovereignty and territorial control that become meaningless when managing planetary-scale energy flows. New forms of global governance would need to emerge that can make binding decisions about energy allocation, infrastructure development, and long-term planning while respecting cultural diversity and regional autonomy. Some researchers propose that Type 1 transition might require the development of world government or similar institutions with real authority over global energy systems. Others suggest that advanced artificial intelligence could serve as neutral coordinators, managing planetary energy flows according to agreed-upon principles while remaining above the political conflicts that prevent effective human cooperation. But the history of international cooperation offers reasons for both optimism and concern. Humanity has successfully coordinated responses to global challenges when the stakes are clear and the solutions are technically feasible. The Montreal Protocol successfully addressed ozone depletion through international cooperation and technology sharing. International scientific collaborations have achieved remarkable results in projects like the International Space Station and the Human Genome Project. Yet these successes involved relatively limited coordination compared to what Type 1 civilization would require. The Montreal Protocol addressed a single class of chemicals affecting a specific atmospheric process. The International Space Station involves just a few nations working on a contained project with clear objectives. Type 1 development would require sustained cooperation across every aspect of human civilization for centuries or millennia. The scale mismatch between current international institutions and Type 1 requirements suggest that entirely new forms of global coordination would need to emerge. These might resemble nothing in our current political experience, possibly involving hybrid human-AI governance systems that can maintain consistent policies across timescales that exceed human lifespans while adapting to changing circumstances and emerging challenges. The educational and cultural changes needed to support such governance represent another dimension of the Type 1 transition that extends far beyond technological development. Citizens of a Type 1 civilization would need to understand planetary energy flows, global climate systems, and cosmic development timescales as naturally as we currently understand national politics and local economics. Educational systems would need to evolve to prepare people for participation in planetary management decisions. Understanding the trade-offs between different energy technologies, the environmental impacts of large-scale construction projects, and the long-term consequences of resource allocation choices would become fundamental civic knowledge. Citizens would need to think routinely in terms of geological timescales and cosmic significance. Cultural narratives and social institutions would need to adapt to provide meaning and purpose for individuals participating in projects whose ultimate goals might not be achieved for hundreds of years. Traditional human motivations evolved for immediate social groups and short-term objectives. Maintaining engagement with multi-generational cosmic projects requires new forms of meaning-making that connect individual actions to species-level significance. Religious and philosophical frameworks are already beginning to grapple with these challenges. Cosmist movements that emphasize humanity's cosmic destiny provide meaning structures that could support long-term space development. Effective altruist philosophies that focus on maximizing welfare across vast populations and timescales offer ethical frameworks for evaluating cosmic development choices. Transhumanist movements that embrace technological enhancement of human capabilities provide visions of how we might adapt to the challenges of cosmic civilization. But these emerging frameworks remain minority positions within broader human culture. The majority of human institutions and belief systems still operate according to assumptions that made sense when our species was confined to a single planet, with no awareness of our cosmic context. The transition to Type 1 civilization would require these assumptions to change across entire populations, not just among technological elites. The timeline for such cultural evolution remains highly uncertain. Major worldview shifts typically require generations to complete, as new perspectives gradually replace older ones through education and generational change. But the urgency of current existential risks might not allow for such gradual transformation. We might need to achieve unprecedented rates of cultural adaptation to match the pace of technological change. The role of mass media and digital communication in accelerating cultural change offers some hope for rapid worldview evolution. Ideas that once took decades to spread across populations can now reach global audiences within hours. Social media platforms and online communities enable the rapid formation of shared identities and values around cosmic development themes. Virtual and augmented reality technologies could potentially provide direct experience of cosmic scales and long-term thinking that makes abstract concepts more psychologically accessible. But the same technologies that could accelerate positive cultural change also enable the rapid spread of misinformation and the fragmentation of societies into incompatible worldviews. The polarization and epistemological chaos that characterize current digital communication could prevent the shared understanding necessary for Type 1 coordination rather than enabling it. The challenge facing humanity is developing communication technologies and cultural practices that enhance our collective intelligence rather than fragmenting it. We need systems that can help billions of people understand complex global challenges and coordinate responses across cultural and political boundaries. The success or failure of this cultural coordination might prove as important as any technological breakthrough in determining whether we achieve Type 1 status. As we consider these vast challenges and possibilities, it's worth remembering that every cosmic journey begins with individual choices and small-scale actions. The research scientist working on fusion energy today, the engineer designing more efficient solar panels, the educator teaching students to think about long-term consequences, all of these immediate activities contribute to humanity's potential progression on the Kardashev scale. The next few decades will likely determine whether our species possesses the fundamental qualities needed for cosmic significance. The decisions we make about energy research, space development, artificial intelligence, and international cooperation will establish the trajectory for everything that follows in humanity's relationship with the cosmos. We might be living through the most important period in human history, the brief window when a young civilization either develops the wisdom and capability needed for cosmic development or fails to navigate the challenges of technological adolescence. The outcome will determine not just the future of our species, but potentially the role of consciousness itself in the ongoing evolution of the universe. The universe has waited nearly 14 billion years for intelligence to emerge and begin the process of cosmic development. Whether that process continues depends on the choices we make in these precious moments when humanity first glimpses its ultimate destiny among the infinite stars scattered across the vast darkness of space and time. So here we stand, at the threshold of cosmic significance, our species balanced precariously between transcendence and oblivion. We've journeyed through the mathematics of energy mastery, witnessed the engineering marvels that await us among the stars, and confronted the sobering reality that we might be living through the most critical period in human history. The Kardashev Scale isn't just a classification system for distant civilizations. It's a mirror that reflects our own cosmic potential and the choices that will determine whether consciousness flourishes throughout the universe or remains forever confined to isolated worlds scattered across the galactic darkness. From our current position at Type 0.73, looking up at the vast hierarchy of cosmic achievement that stretches before us, the journey seems almost impossibly daunting. The fusion reactors we need to master, the space-based infrastructure we must construct, the artificial intelligence we must align with human values, the international cooperation we must achieve across centuries of sustained effort. Each challenge would represent the greatest undertaking in human history, and we need to solve them all simultaneously while racing against existential risks that could end our cosmic story before it truly begins. Yet perhaps that's exactly what makes this moment so extraordinary. We're the first generation in human history to understand our place in the cosmic order, to glimpse the vast possibilities that await intelligence in the universe, to realize that the choices we make today could echo across millions of years and billions of stars. Every breakthrough in energy technology, every advance in space exploration, every step toward greater global cooperation moves us infinitesimally closer to joining the ranks of cosmic civilizations. The universe has waited nearly 14 billion years for matter to organize itself into patterns complex enough to contemplate their own origins and destiny. Through us, the cosmos has achieved something remarkable. It has developed the capacity to understand itself, to dream of reshaping itself according to conscious values, to envision futures where intelligence guides the evolution of entire galaxies. Whether we realize that extraordinary potential depends on the wisdom, courage, and cooperation we demonstrate in the critical decades ahead. The next chapter of the cosmic story is being written right now, in research laboratories and international conferences, in classrooms and boardrooms, in the countless individual choices that collectively determine humanity's trajectory toward the stars. The Kardashev Scale reminds us that we're not just struggling for survival on a single world. We're participants in the universe's greatest experiment, the attempt by consciousness to transcend its humble origins and become a permanent feature of cosmic evolution. The outcome remains uncertain, but the stakes could not be higher. Tonight, as you look up at the stars scattered across the darkness above, remember that you're gazing into humanity's potential future. Those distant points of light might one day be surrounded by the energy-harvesting megastructures of our descendants. The galaxy itself might someday bear the fingerprints of human engineering on scales that dwarf our current imagination. But that future isn't guaranteed. It depends on choices we're making right now. In this brief moment when consciousness first glimpses its ultimate possibilities among the infinite stars, the universe waits to see what we will choose, and the answer will determine whether intelligence flourishes throughout the cosmos or remains a fleeting whisper in the eternal night. The journey toward cosmic civilization begins with a single step, and that step starts with us.